In this video, we explain the fundamental concepts of static pressure, velocity pressure, and total pressure in the realm of HVAC systems. Understanding these pressure components is essential for designing, maintaining, and optimizing air conditioning ducts. In this video, we will explore the definitions of static, velocity, and total pressure, their significance in HVAC engineering, and practical insights on the instruments commonly used to measure them. Atmospheric pressure. Atmospheric pressure is the force exerted by the weight of the air above a specific point on the Earth's surface. It is the pressure exerted by the Earth's atmosphere on objects within it. At sea level, atmospheric pressure is approximately 14.7 psia, pounds per square inch absolute, or 1,013 millibars. Atmospheric pressure decreases with altitude. HVAC systems in high altitude locations may require adjustments to account for lower atmospheric pressure, affecting factors such as air density and combustion processes. Using a U-tube manometer, with both ends open to the atmosphere, the liquid level on both sides of the tube rests at the same height. This is because both ends of the tube are open and exposed to the same atmospheric pressure. Static pressure. Static pressure is the pressure exerted by the air in all directions within the ductwork when it is not in motion. It is a measure of the potential energy of the air as it remains static or stationary within the system. Static pressure is the force exerted by the air on the walls of the ducts and other components when the air is not flowing. It is typically measured in units such as inches of water column or pascals. Air encounters resistance as it moves through the ducts, filters, coils, and other components. This resistance generates static pressure. When choosing a fan for an HVAC system, consideration must be given to the static pressure the fan must overcome to deliver the required air to the space. The layout and design of the ductwork, including bends, transitions, and fittings, can contribute to static pressure. High static pressure can lead to increased energy consumption, as the system must work harder to overcome resistance. Static pressure affects the airflow within the ducts. Excessive static pressure may result in reduced airflow, impacting the system's ability to deliver conditioned air to the desired spaces. Velocity pressure. Velocity pressure is the measure component associated with the movement of air within a duct. Consider a scenario where a fan is propelling air through a duct system. During this process, two distinct pressures come into play: velocity pressure and static pressure. The combination of these pressures is termed total pressure. Velocity pressure arising from the movement of air can be quantified by determining the variance between total pressure and static pressure, with pressure units denoted in inches of water or pascals. Direct measurement of velocity pressure is not done. Instead, the most straightforward method to ascertain the airflow velocity is by assessing the velocity pressure within the duct using a pitted tube assembly linked to a differential pressure sensor comprising both a static pressure probe and a total pressure probe. The pitted tube can be inserted into the airflow to measure both static and dynamic pressures. The dynamic pressure measured by the pitted tube represents the velocity pressure. Total pressure. A total pressure probe positioned in line with the airflow detects both the duct's velocity pressure and static pressure, resulting in the total pressure. Meanwhile, a static pressure probe, oriented perpendicular to the airflow, exclusively measures static pressure. The disparity between the total pressure reading and the static pressure reading represents the velocity pressure. If you like that video, please give it a thumbs up and subscribe to our channel. Thank you.